Hey guys, this is our first lesson of this new unit. It's a very, very short unit, pretty much factoring. And so we're going to do a lot of factoring, a little bit of solving quadratics, but this lesson is just strictly about can you factor. So we're going to go through a few different types of factoring, which should remind you of all the stuff that you should relatively know how to do. So first up, what are factors? Got to know what that means. Factors are the numbers or terms that can be divided out of a single or collection of larger terms. So the example, 24 has factors 8 and 3, and they are a factor combination that would make 24. Now, there are two different things that you need to be able to do, pretty much, for factoring quadratics. We need to be able to list all the possible factor combinations, and it's a good idea to know how to do prime factoring. So for all the possible factor combinations, it's just a matter of kind of knowing your times tables. So to make 24 is 1 times 24, 2 times 12, 3 times 8, 4 times 6, 5 doesn't work. Which, if it doesn't work, don't write it so you don't confuse yourself. 6 works, 6 and 4, 8 and 3, 12 and 2, 24 and 1. Notice how that once you get halfway through, it starts repeating itself, and so you really don't need that bottom half. What we found here are all the possible factors, as well as the all the possible factor combinations. Okay. Now, prime factoring is slightly different. We do a number tree where I put prime numbers on the left, divide them out, and you want to start with the lowest prime numbers that you can. So 2 is a prime number, and we keep on going until we can't divide by 2 anymore, and then you know you're done when all the branches end in prime numbers. So 2 times 2 times 2 times 3. Okay. Both these things are important for doing GCF, as well as doing just regular factoring in general. So here's the factor tree I was just mentioning, so just another example of it. Now, we're going to do factoring binomials with GCF. So a binomial is a set of two terms that cannot be combined. So this is our example, 2x to the fifth plus 6x squared. Factor a binomial, you divide out common factors from each term, treating the numbers and variables separate, and use parentheses to separate the factor from what is left. So you want to look at the numbers and the variables separately. So if you look at both the numbers 2 and 6, they can both be divided by 2. So I put a 2 on the front, and then I'm left with nothing in the first number. It's just 1. And then 6 divided by 2 is 3. So that's where the 1 and the 3 come from. With the variables, you want to know how many they have in common. So they both have x's, but this one over here has 2 x's, whereas this one has 5 x's. So I can remove only 2 of them, leaving 3 left over in the front and none in the back. Now, if you want a more visual way to do that, you can do prime factorization. That's 2x to the fifth. 6x squared would be 2 times 3 xx. So 6 turns into 2 times 3. We see they both have a 2 and 2 x's, and then you see what's left. X to the third power and a 3. So the 2 and the 2 x's go out front. Left over with xxx plus 3, do some condensing, and you're good there. So you should do GCF at the start of every single possible problem, if it is possible. It's not always possible, but if you don't do it at the start, you're going to have to do it at the end anyways, and then throughout that, you will have much larger numbers and probably make it way too hard on yourself. Okay, trinomials is what you're probably used to. They're quadratics for the most part. So a set of three terms that cannot be combined. So there's an example, x squared plus 7x plus 12. More often than not, this will present itself as a standard quadratic equation whose factored version will be some combination of binomials. Okay, an x plus or minus something, and then an x plus or minus something. Now, there are a variety of levels of difficulty depending on how the problem is set up. And it all revolves around whether or not there's a number in the front. If there is not, all you have to do is all the factor combinations of 12 and then find one that combines to make 7. So the example, let's see, to make 12, we have 1 and 12, 2 and 6, 3 and 4, and then it repeats. And then it's the 3 and 4 that add up to make 7. Oops, well, you get the idea. Okay, could be x plus 3, x plus 4, or x plus 4 plus 3. And that's the easiest type. You know, there could be negatives, could be big numbers, but that's pretty much the easiest type. And then we're going to look at some where there's an extra number there, and you'll see how much more difficult that is. If you're ever unsure, okay, there's hundreds of thousands of YouTube videos, tutorials on how to factor, so please use your resources. Okay. So let's go through a few examples. Okay, notice how there are different numbers in front of each one. And then number 4 even has a number missing, and so we'll get to that when we get to that. And let's just start with the easiest. So number 1, notice the minus signs. The minus signs means we are going to subtract to make 6, not add. So 16 has the factors 1 and 16, 2 and 8. So I found my pair already, because 2 and 8 will subtract to make 6. Now the question is, do we want 2 minus 8 or 2 plus 8? Or sorry, 8 minus 2 or 2 minus 8. So that 6 is negative, so it's the bigger number is negative. And we jump straight to our answer. Okay, no more work required. Number 2, there is a number in front, but we can get rid of it. Remember I said to use GCF if at all possible, and this one has a GCF. So I can divide all three numbers by 4. And when I do that, I'm left with r squared plus 2r minus 80. And I want, let's see, it's negative, so I want two numbers that combine to make 2. So I think that's going to be 10 and 8. 10 minus 8 specifically. So jump straight to your answer. Now, if you couldn't think of 10 and 8 off the top of your head, go ahead and list all the factor pairs. Oh, let's see. Number 3 has a number in front, but I cannot get rid of it because I cannot divide all three numbers by 15. What I can do is divide them all by 3. So if I divide them all by 3, I am left with 5r squared plus 21r plus 18. Now I have to actually deal with the fact there's a number there, which means it is a lot of extra steps compared to the other problems. So instead of factor combinations to make 18, I need to do 5 times 18, which gives me 90. And I want factor combinations of 90 that make 21. Notice I didn't have to do that in the other problems because the other problems did not have a number in front. So let's see, 15 and 6 are going to make our 90 and also make our 21 in the middle. Instead of jumping straight to the answer, what I have to do now is I am splitting that 21r into 15 and 6. And I split it in a perfect way so that when I factor by grouping the two sets of binomials, I'll be good. So factoring the first set, let's see, GCF is 5r, and I'm left with r plus 3. GCF of the second one is 6, left with r plus 3. And we have a repeating parenthesis, which is part of our answer. The other factor is the GCFs that we pulled out. And then the 3 on the front, can't forget that. So notice you can't just jump around to the answer. You have to go through the whole thing, factor by grouping, splitting it up. the works. Okay, this last one, number 4, it has a term missing. You can factor it using a 0 for that term, but instead it's just a good idea to say, hey, this is a difference of squares. It is something squared minus something squared. So whenever you have that, you take the square roots. Let's see, square root of 9k squared is 3k, square root of 25 is 5, and write both plus minus versions, and then you're done. That's all you got to do. Don't overthink the difference of squares. Make sure you can recognize that it's a difference of squares and just do it that way. Okay. Some more for you to practice. I'll leave those 4 up to you. And let's see. Let's go ahead and go on. So, difference of squares, like I mentioned, if it's something squared minus something squared, you do the square roots, x plus 2, x minus 2. The bottom one doesn't look like a difference of squares initially, but remember what I said, if you can take out a GCF, you do. They both have x's, so I can take out an x squared, left with 16x squared minus 9, which is a difference of squares, so 4x plus 3, 4x minus 3. Okay. So sometimes it's obvious, sometimes not so much. You might have to pull out a GCF to be good. There is such a thing called the sum of squares, but we are not going to worry about it anytime soon. That's about 6 months from now because it requires imaginary numbers. There's also such thing as the difference of cubes, sum of cubes, and other formulas. We're not going to worry about anything higher than difference of squares. So if you see a plus sign, don't worry about it. Another special case, whenever you're given 4 terms, it's a factor by grouping problem. It can present itself in a couple of ways. The top one is a cubic. None of those terms can be combined, so we do factor by grouping. So let me try and squeeze that in here. Let's see. That one is 4x squared, leaving you with 7x plus 1. Over here, I can factor out a negative 5, leaving me with 7x plus 1. So my factored combo is 4x squared minus 5, 7x plus 1. Okay, bottom one, same thing. However, don't get caught up in the fact that it looks like you can combine those two things in the middle. Yes, you could, but then you'd be backtracking, and you don't want to have to do that. So don't combine stuff if you're given 4. Just do factor by grouping. Let's see, on the front, 3x, leaving me with x minus 3. On the back, GCF is 4, x minus 3. And I've got x minus 3, 3x plus 4. So really, whenever you're given 4 terms, you're just doing that last step or two from the regular hardest factoring difficulty ones. Okay, and that's essentially it. We went through all these extra problems in class here, so I'm not going to go ahead and list them all on here right now because you should be able to, take a look and see how you do. But otherwise, that's the end of this lesson, and I'll see you guys in class.